Hello. Today I will talk about the way to deal with bound state systems with an effective field theory approach. We will consider hydrogen atom, muonium and positronium. Also, we will learn how to evaluate the energy levels corrections due to field theory in these systems, as well as the positronium decay widths. First, I will remind you about the hydrogen spectroscopy in non-relativistic quantum mechanics, relativistic quantum mechanics and field theory. After that, we will look on the lamp shift correction in effective field theory approach. Then I will describe the velocity renormalization group, and we will learn how to evaluate the logarithmic corrections to energy spectrum and decay widths within this renormalization group. Okay, the hydrogen-like systems can be solved in non-relativistic quantum mechanics by Schrödinger equation in Coulomb field, and the spectrum of the system is the same as in the simple Bohr theory. It depends only on one integer number n which goes from 1 to infinity, and this number is called principal quantum number, and in this case it's independent on angular momentum and on the spin of electron. If we will account the relativistic nature of electron, we have to solve the Dirac theory in the static Coulomb potential, and the solution will now depend not only on one integer number n, but also on the total angular momentum j, which is also integer number. And the splitting between levels with the same principal quantum number but different total angular momentum is called fine structure. The value of this splitting is suppressed by order alpha in comparison with the splitting between levels with different n. And that was the historical reason to call electromagnetic constant fine structure constant. But in 1947, the experiments of Lamb and Rutherford shown that there are two different levels with the same quantum number n equals 2 and j equals 1/2. These two levels correspond to different angular momentum of the electron and such shift called lamp shift. On this figure you can see lamp shift and fine structure constant. On the left plot the n equals 2 levels for hydrogen are shown. We can see here that the lamp shift is much smaller than fine structure, and the difference between 2p1/2 and 2p3/2 levels, and in this case the main contribution to the lamp shift is given by the vertex correction. On the right plot the same levels are shown for the muonic hydrogen, and in this case lamp shift is much larger than fine structure. The main contribution to the lamp shift here comes from the vacuum polarization, which is enhanced by the muon mass in case of muonic hydrogen, and also the interesting point that it has different sign. I want to note that lamp shift is quantum field theory effect, and in case of just Dirac equation we have no such difference between levels. On these figures you can also see a so-called hyperfine structure, which distinguishes between different orientation of lepton and proton spins. Today we will evaluate the leading contribution to the lamp shift in electronic hydrogen, and we will also look how to obtain the leading logarithmic contribution to energy levels corrections in the case of muonium and positronium. First of all, the distinctive feature of hydrogen-like systems that we have very well separated scales hierarchy. Mass of the proton is much larger than the mass of electron. Of course, it's not the case of systems like muonium or positronium, where we have to deal with recoil corrections. But for the case of electronic hydrogen, we can create proton as a static source. Then the momentum of the electron is suppressed by 1 power of alpha in comparison with its mass, and the energy spectrum is suppressed by 1 another power of alpha. So we can first match quantum electrodynamics to the non-relativistic quantum electrodynamics when we deal with non-relativistic momenta of electrons, and after that we can integrate so-called soft photons, which momenta of and energy of order m alpha, and we will left only with ultrasoft photons of energy m alpha squared, and we can look on the contribution of these ultrasoft photons to energy levels corrections. So we have two top-down effective field theories, and we have to do matching 2 times. And at the end we can evaluate energy levels corrections in the so-called pNRQED, or potential non-relativistic quantum electrodynamics. So the first step is to obtain non-relativistic quantum electrodynamics from usual quantum electrodynamics. We will work up to the order alpha to the 5th, and the kinetic term can be written quite simple for proton, which is created as a static source. Of course, we do not account here recoil corrections, which can be a good approximation for electronic hydrogen, but it's not a very good approximation to do precise physics. Then we expand the electron kinetic terms in powers 1 over c and keep the only necessary to order alpha to the 5th terms. The interesting point about this expansion is that the Wilson coefficient cycles 1 at all orders, because QED is renormalizable theory. Also, we will have the interaction between electron field and the photon field, which we look like non-relativistic photon field, and of course we'll have the kinetic term for the photon field. From the beginning we can set d1 equals 1, because it means just the redefinition of charge and or low energy constant of this theory. The obtained Lagrangian works for non-relativistic external lines and also for non-relativistic momenta in loops. This Lagrangian respects all QED symmetries, and also it respects Galilean invariance. The feature of this Lagrangian is that it does not account recoil correction, and it does not describe the spin physics in a correct way. The Wilson coefficients are obtained from pNRQED1 loop matching to QED in dimensional regularization at scale mu. The coefficient CF describes the anomalous magnetic moment of the electron. This coefficient D corresponds to the Darwin term, and CS to the contribution of Seagal graphs, and the coefficient D2 is just coefficients from the earlier Heisenberg Lagrangian, which describes light by light scattering. This Lagrangian is written in terms of Pauli spinors, which are non-relativistics, and so we can apply all the machinery of non-relativistic quantum mechanics to this system, which can be simpler than the usual quantum field theory approach. The next step is to integrate out the photons of scale m alpha and to obtain pNRQED. We can create here electrons for matching as HQT wave functions. First of all, 2-point functions are insensitive to the relative momentum, and so they will have the similar kinetic terms for electrons, photons, and also for static. further. But 4-point functions now know about the relative momentum, and so they arise, and this describes the potential piece. The size of the bound state is of order 1 over m alpha, while the energy of ultrasoft photons is of order of alpha square, so we can multiple expand ultrasoft photons in electron nucleon Green's function. pNRQED has no energy scale, so any loop will give 0, and NRQED calculation directly give us the potential. So, but to deal with bound states, we have to project this field theory to the bound states of space. We will obtain it by expansion of Lagrangian up to the order alpha to the fifth. From the nucleon we will have only delta function because it's treated like a static source. We will have the same kinetic term but now with usual derivatives, not covariant, and we will have the potential piece of interaction between electrons or our bound state and ultrasoft photons. This potential is not gauge invariant, but we can restore gauge invariance order by order looking on ion field, which is defined by the following way. It transforms under gauge transformation as with the power z minus 1, and that is the reason why it's called ion field, because the electron field transformed is exponent to the power 1. Okay, so the Lagrangian for this ion field will have the same kinetic term, but the potential term will be different, and we can see gauge invariance from this term. So we have written the Lagrangian for potential non-relativistic quantum electrodynamics, and the easiest thing to do is to evaluate the contribution of potential terms to the lamp shift. First of all, we found the states of bound system by solving the Schrödinger equation for hydrogen atom, and we have found Schrödinger wave functions. The contribution to the lamp shift from the soft photons have following terms. First of all, it's the kinetic energy corrections of order p to the fourth. Then the contribution which comes from the Darwin term and also from the earlier Heisenberg Lagrangian, which is correction only for s levels due to the wave function at 0, and also the contribution from the Seagull type of graphs. And the contribution from hard photons is encoded in Wilson coefficients, and so it's also included in these corrections. The next step is to evaluate the contribution of ultrasoft photons to the lamp shift. In the given order, they contribute to the bound states of energy, which changes energy levels. If we will work in Coulomb gauge, then the contribution from a zero component of electromagnetic field will be 0. In the Coulomb gauge, a 0 produces only poles graphs, which vanishes in dimensional regularization. So we will have only the following vertex, and in each vertex we have to include the factor of velocity. The shift of energy levels can be defined from the Green's function, two-point Green function in momentum representation in the limit when the momentum goes to one of the energy levels, and we can obtain the energy correction from the second term of this expression. And during the evaluation we will have integrals with photon propagator, projection to Coulomb gauge, and also the propagator of bound state. This integral can be evaluated in dimensional regularization. We prefer dimensional regularization because before we used also dimensional regularization for matching. The divergent piece of this integral can be included in the Darwin type counterterm, and the subtraction point dependence will cancels with the subtraction point dependence in Darwin-Wilson coefficient. And we left here with the sum over all energy levels and with logarithm of mass over scale of order mass times alpha. And this is so-called famous beta logarithm, which was obtained by beta, and in principle it can be evaluated to any accuracy we want if we will include more and more energy levels in this sum. So we have obtained the lamp shift correction from the effective field theory approach in two stages. First, we have integrated out hard photons, and then we have integrated so-called soft photons, which energy of order mass of electron times alpha. We left with pNRQED, and we found correction in this theory. We found that beta logarithms come from the contribution of ultrasoft photons only, and also we have reproduced the results of previous calculations. The other way to reproduce leading logarithmic corrections is by running of coefficients of effective field theory in renormalization group, which called Velocity Renormalization Group. This is one stage velocity running, and soft photons and ultrasoft photons operators run simultaneously. The only difference that we are running now on velocity rather than alpha, and that there are two different scales for soft photons and for ultrasoft photons. We run from velocity equals 1, which corresponds to higher energetic electrons, to some scale v, and in one stage. If we will run in two stages, we will obtain the different result. However, for the case of the constant anomalous dimensions, which is the leading order corrections, these two runnings are equivalent, and that's why we will obtain the right result of order alpha to the fifth log alpha as a contribution to the lamp shift. But with two-stage running, we can reproduce also alpha to the 6 log alpha, alpha to the 7 log squared alpha, and alpha to the 8 log to the cube alpha series, and also we can found that this series terminates. We have now two small scales, alpha and v, so the power counting should account for both these scales. We will denote the potentials in powers of v, and the odd potent terms here comes from tree-level matching, but even terms obtained only at one loop. The leading potential is Coulomb potential, v minus 1, and the next one is obtained only in one loop, and the potential of order v is following, where lambda depends on spins of particles and also on the total spin of system. Potentials are for fermion operators in comparison with kinetic term, which are two fermion operators. That's why the naive order, for example, for Coulomb potential as alpha over v squared is different, and in power counting it enters like alpha over v. The power counting of other terms can be determined in relation to the Coulomb potential, and on the following table we have shown the power counting in two variables, alpha and v, and the resulting order of magnitude in terms of alpha, and the correction to the energy levels which comes from these potentials. So we can see that Coulomb potential is of order 1, that's why it cannot be created perturbatively, and it has to be solved in all orders by the solution of non-relativistic bound system problem. We define the leading order and next to leading order running relatively to the potential power itself, and for example the leading order running will correspond to n equal 1, and the next to leading order running correspond to n equals 2. The leading order running can be described quite simply because the Coulomb and V1 potential as well as structure constant do not run in this order. So the first running coefficient will be U2. The Renorm group equation is determined from anomalous dimensions for potential V1, and the first term in this equation corresponds to the contribution of soft photons in the left graph, and also we'll have a contribution of ultrasoft photons with all possible permutation of legs, which is given by the second term. Since the right hand side of this equation is constant, we can rearrange variables, and we can write our Renorm group equation in the following way. The solution is pretty simple, and to obtain the correction to energy levels we have just to multiply this solution by the wave function at 0 squared, which will give us the correction of S levels and therefore lamp shift. If we'll multiply just logarithmic term, we will obtain the beta logarithm, but here we have accounted for recoil corrections, so this result can be used not only for hydrogen but also for muonium or positronium. The interesting thing about this result is that in the leading alpha to the fifth order we have only contribution from log but not log squared or log to the third, so it's proven that our log series terminates. To obtain the next leading order logarithmic corrections to energy levels, we can solve a Renorm group equation after substituting the leading order running in the right hand side, and next to leading order series are also terminated by log to the cube alpha, and with this series we can predict the coefficient near, for example, alpha to the 8th log to the cube alpha term in the lamp shift, and also with the count of all recoil corrections, which was very different to do without Renorm group equation. Also, it's possible to predict the contribution to the hyperfine splitting of S level, which is of order alpha to the 7th log squared alpha. And if we will create the imaginary part of energy contribution as contribution to the decay widths, then we can also evaluate the positronium decay widths of order alpha squared log alpha and alpha to the cube log squared alpha. But to do it we have to modify our potential, including the possible annihilation graphs of positronium to 2 photons and 3 photons, which will give imaginary parts. So to summarize, we have studied the atomic spectrums like in hydrogen atom, muonium and positronium, and the contribution to the lamp shift hyperfine splitting. In terms of effective field theory approach, we have evaluated the leading order contribution to the lamp shift, which is alpha to the fifth, and also we have reproduced the well-known beta logarithm that is given as contribution of ultra-soft photons. And within the Velocity Renormalization Group, we have seen the way to obtain the leading logarithmic contributions at given order to hyperfine splitting and also to lamp shift. We have reproduced the beta logarithm. Also within this approach, it's possible to see that logarithmic series terminates, and it's possible also to find the contribution to the decay width of positronium. So thanks for your attention, and here are the references which I have used during the preparation to this talk.